Yeah, so then I'm going to share a few slides to give you a summary of where the status of the MagNet challenge. Let me turn on my sharing so that I feel like because we're running this as an open source community, nothing cannot be shared. So I will share the information we have. So right now, as I mentioned, we received 25 submissions and we performed our code review. And fortunately, most of the code are executable. So we were able to get exactly the same results as the team submitted. And we have shared a self-evaluation kit to all of the teams so that you can do your own evaluation on how the model performance looks like. And also you can go ahead and then improve your model if you are targeting a publication or you are submitting a paper. So now you have 15 materials to present. And then this will keep going. We are continually measuring new materials. And as I said, I hope the software tools that you develop through the challenge will really be useful in the future because it can we can keep improving it. And ultimately, the short-term goal is maybe after the challenge, after we finish selecting the winners, for the 15 materials that we already have, we can create a standard model. Like we have the ranking of every team for each material for all of the 15 materials. So we are going to invite, if your team's performance is really good for a particular material, we will invite you, and then we'll create a software tool, maybe in MATLAB or in Python, so that everyone can call it. And that could be a standard core loss prediction model for now. And if there are better models emerging, we are happy to replace it, or maybe you can open source it from your side yourself. So I guess a community effort is really interesting and exciting. Yeah, so I'll do a very brief presentation. Many of you have seen these slides. The motivation of this challenge is to upgrade the Steinmetz equation, which has been there for 100 years. And 2023 was the 100 years since after Steinmetz passed away. And it's really a time for us to think about how do we develop better tools to predict core loss for a given excitation. And I would say when I was presenting this a couple months ago, we talked about improving the model or upgrading the model. So we saw good attempts to either improving the Steinmetz equation or jumping out of the Steinmetz equation and the hybrid of the both, like using Steinmetz equation to make the neural net model more predictable. So there are a lot of very interesting concepts. We have asked many of the teams whether they want to open source their model and their results and their reports, and many of them responded yes. So after we finish the judging process, we will work on it and open source all of the models and reports so that you can see all the interesting ideas. And as I mentioned, one of the possibility we are thinking about is we can write a review paper or article to IEEE Power Electronics magazine to report the progress of the MagNet challenge as a team, all of us, so that this is sort of like a review of the challenge. What we find as useful, what do we find as not so useful, what do we find as the gap, and what are the remaining problems to solve in the future. So these are all ongoing possibilities. What I want to say is that MagNet challenge is not the end, it's just a starting point. So I don't think we need to present this. This is just the rules. What we're trying to do is for given B excitation, a frequency, and a temperature, how can we develop an algorithm to predict the core loss based on limited data coming from measurement? That's the general setup for this competition, which we believe is what we are facing in the real world scenario, where you may have an arbitrary excitation running at a particular frequency and temperature, but you only have limited data for this new material. But you may have a lot of data for the old materials, existing materials. So how do we make use of all the information that we know to understand the new material with limited new data? That's the general setup of this challenge, and that we find a very good success, as we're going to see later for the result summary. So if you are staying with the MagNet challenge, we started about March 2023. We launched the challenge We have 40 teams from 17 countries registered for the competition. And then we run a few tutorials over the summer. And then we have the qualification, which include 25 teams from 14 countries. And then we have the final submission, including 24 teams from 14 countries. And then in January, we performed our code review and report evaluation. And before February, we're aiming end of January, early February, we will try to select the final winner. And also, we highly encourage you to attend APAC, and we'll try to get our results as soon as possible so that hopefully we can get most of the team to be represented at APAC. But let me make it clear, like whether you come to APAC or not has nothing to do with whether you will have a chance to win or not. So it's not really related. If you can't come, that's fine. Yeah. So these are the teams, 40 teams for the registration. These are the final submission teams. 24 teams submitted the final results. We are very excited. And these are the organizing committee of the people who contributed to the challenge in some way. And some of them actually haven't seen the final report yet. We are prioritizing our judge committee, make sure they are informed. And after that, we'll reach out to more people to look at the results and give us feedback. The awards, we have a total budget of 55,000, which is a pretty big budget. 30,000 come from Pels, and 25,000 come from industry support. So we can freely allocate the money. We can save the money for future. We can spend all the money. But right now we are thinking about 2 awards for the model performance, 2 awards for model novelty, 1 award for outstanding software engineering, and meaning honorable mention. We may move the honorable mention into like 3rd place for performance or 3rd place for novelty. So these are pending decision from the judge committee. So for the model performance, the criteria is fairly straightforward. It's the accuracy, which is just the number. And then it is what it is. And there's a model size. We verified all of the models. And if there's discrepancy, we have reached out to the team and corrected. So we think we have a very good understanding of the model performance and parameter size. And it's the judge committee to decide who made the best trade-off. For the novelty, it will be both, right? So a model which is very novel, but performance was not great, certainly won't be qualified for the novelty. In order to win a novelty award, you need to provide reasonably good performance. And then within the teams which achieves reasonably good performance, we will give out a few novelty awards, which will again decided by the judge committee. And we'll certainly provide comments, and then they will make a decision. And it's basically whether we think your method can become a standard method for creating a model for a new material. So that's our criteria. So we try to make it more like a real world scenario, assuming a company released one very good material, but they don't have a way to characterize the loss or model the loss or create a data sheet for the loss. So we are looking for a method which has the highest possibility of being adopted as a standard for modeling this particular material. So that's our criteria. So we will look at whether your model can be generalized for those. And also we are looking for novel concept that may help us to understand better physics. So whether your model is providing new insights, and at the same time give you reasonably good performance. So novelty is a little bit more of a gray area, and we may end up giving novelty award without the ranking because it's just very hard to rank which one is more novel. So maybe we'll give out maybe 2 or 3 novelty award, but without providing a rank. So that could be possible, or depends on how does the judge process go. So beyond that, I would say money is just one thing. Honor is important, but we're trying to solve scientific problems. The more important or more exciting outcome of these competitions, really, we can create a standard model which is certified by many people with a lot of data. This is the material that you can use for a particular material like M49 CT90. These are very commonly used NAND materials by industry, and we can say to them, hey, there's a better model that you can predict the core loss, and feel free to try it. And I hope that many of the teams now, you have the infrastructure, software infrastructure, and some of you even build a hardware infrastructure. So you can join us. Now you can create your own new data. And maybe sooner or later, we can have a few tens of materials covered. Then really, really, core loss problem is solved. In terms of IP, we made it very clear that when you are submitting your code and report, it's effectively public disclosure. Think about it as a conference. So when you are submitting a report, it's basically you already disclose it to public. So we don't have any restriction on IP. So if you want to file a pattern, you should have already filed it. If you want to publish a paper, it's the same thing. So you can keep publishing, you can improve your results, and then submit to conferences and journals. Yeah, and whether you want to open source or not open source your code is your decision. But I have asked many of the teams whether you want to open source. If you want to open source with us, we'll be happy. So what my plan is for the teams who choose to open source with us. So we'll create a folder in the GitHub and then put your name there. So this is the model coming from a particular team. So that's the way how it works, but we want to run it in a open and transparent way. But it's your decision whether you want to release it or not, and that's not related to the result of the challenge. Yeah, so competition rules. We want to make it a little bit clear. Now we can freely talk about everything. So for the stage 1, we provided a lot of data for 10 old materials. And many of you are familiar with it, and some of you are really studied carefully. And we're very impressed in how much details you guys dig out of each of the material. And some of you have a material matching process. Like if a new material comes, you first compare whether this material looks like which material that exists, and then you start to train your model, develop your model based on the material that looks most likely look like your new material. That's a really good concept, and that's what we think should be happening. We're very happy to see those methods. And then for the find new material, we intentionally make it like a challenge, right? We have a lot of data, yes, but we only give you a little bit of data. That's most likely the real world scenario. So all of the teams are given limited data for 5 new material, and then we use a lot of data we keep it private for testing. So we have 5 materials, and we sample them in different way. So for material A, which is 3C92, now you have the real information. It's 3C92. We call it tiny data challenge, meaning that this material looks very much like a standard material. Looks like very much like a typical material you'll see. And as a result, we think you just need to train a model with a small amount of data. So we intensively downsize the data. So maybe we only provide 10% of the data we have and use 90% for testing. For material B, it's a unique material challenge. It's a material which has interesting behavior regarding temperature and frequency and DC bias. It looks a bit different from other materials. So that's why how we sample. We provide a little bit more data. For this, we provide more training data and less. You can see more training data and less testing data for this material because it's like a new material with very interesting behavior. There's temperature challenge. Material C it has an interesting temperature behavior. I believe it's either going straight up or going straight down, or you may have optimal ones in the middle. I'm not exactly sure. Maybe Haoran can correct me later. So it's a material which has an interesting behavior as the temperature change. And again, we sampled it in an interesting way and then see how the model behave. And then material D, it's 79 from ferrite. It's a waveform challenge. We intentionally only give you sine data and triangle data, but we didn't give much trapezoidal data, and some of the team realized that. And that's very interesting. And most of the teams has the worst performance in material D. So if your team did well for material D, that's very impressive because that's In our opinion, it's very challenging because you are only given sine and triangle, but not trapezoidal, and that means your model is very generalizable for different type of waveforms. And finally, material E is a frequency and flux density challenge. We intentionally take out a few frequencies and a few flux densities, so there's a gap in the entire frequency and B space. And we intentionally do that so that to test your models generalize whether your model is generalizable for frequency and B. So that's the background of the competition, and we try to make it more like real world. Again, real world scenario. You may face all of these challenges when you are dealing with a new material, and we try to test your model in different ways. Any question? Happy to discuss. I have a few more slides, but I want to pause here a little bit and initiate some discussions. No, everyone clear? Okay, great. Now it's the result. So I was hesitating whether I should correlate the team names and the ranking and performance here, but then I decided we are open source community. Everything is just a fact, and we're not making it public. So if I will make it clear that the models that this is a competition, it's a game. The models that winning model may not be necessarily the best model. The model which didn't get the best result may not necessarily be not the best model. So really, this is a game. Your model is winning because it's winning in this particular scenario. That doesn't mean that in other scenarios the model is always good, and vice versa. If the model didn't perform so well in this particular setup, it may perform well in other setup, or maybe it's best model for us. So don't think about the ranking or the performance by too much. And also different teams put different resources. Some teams has 7 people, and other teams maybe have 1 or 2, and different the schedule and agenda of different universities at different places of the world is different. And December may just be a very difficult time for many teams. So I would say don't put the ranking into it too much. This is just a start. But I'm happy to sort of like, this is how we evaluate all of the teams. So there are 5 materials. We will evaluate the 95% error for each material and take an average of that. This is a average error for each of the team and average model size. And then for all of the 5 material. And as I said, the 5 materials are designed for testing a model from different purposes. And then what we do is we sort of rank it. Although I said rank doesn't matter, but for the purpose of the competition, we have to sort of rank it and get a sense. And some teams, this number 1 means that you're doing well. It's like gold medal for this particular material in terms of accuracy or size. And number 2 is silver medal, and the green is number 3 is the bronze medal. So many teams has good medals there, but if you're not winning, that doesn't mean that your model is not good. Maybe your model is just great, but doesn't fit for the particular setup of this competition, or unfortunately, the materials that we choose doesn't fit the purpose of your model. So don't read this into this for too much. And then we sort of, there's no way to average across different materials, right? So because some materials we intentionally make it very difficult to predict. Some materials are easier. So, but in order to get a general sense, we sort of averaging the ranking, the average error of across the 5 material, averaging how many parameters you need for each material, and then we create a graph. Looks like an accuracy ranking and size ranking. I would say this graph, this curve is sort of where we are. We're Princeton teams. When we started the competition, we feel like, well, yeah, this is just too much work. And as a single research group, we can't do much. We want to make it open source and encourage more of you guys working with the entire world to figure out this problem. And we're very excited to say that, well, all of you guys, a lot of things have done much better than what my team at Princeton we're doing. So congratulations to all of you guys. We are sort of pushing the boundary all the way forward. Originally, we were talking about tens of thousands of parameters per material, and some of the teams are doing thousands of parameters, and some of the teams are doing hundreds of parameters. So it's very, very impressive. So we can basically now we can say the state of the art of modeling a typical magnet material, you need a few hundred to 1,000 parameters to get an accuracy, single digit accuracy, a single digit error in predicting a core loss. And if you go more aggressive, like these teams, which they try to go with a full analytical parameterized methods, then physics-driven methods, then maybe you can do it with maybe 60 to 100 parameters, and the error then goes to about 15% to 20%. So that's the state of the art, and it's really good that like once only because of you guys that we can now say that, and maybe next year or within a few years, and maybe on the other hand, these models, if we present to the material manufacturer, we can say that used to be the materials are not just not good, so that you cannot develop better model. But now we can say that we have methods to model core loss up to single digit error if the data is good enough. Now the stress goes back to the manufacturer. Can they produce materials that has sample to sample variation smaller than single digit? We don't know. We'll see. But at least we solve part of the problem from the modeling side. We do have very, very powerful models that can precisely model the behavior of the material. It's the problem for the measurements and the manufacturing. Again, don't read into this too much because things may change, and really this ranking depends on how do you averaging this. So the true ground truth is this table. So we believe this table is the ground truth. Your team's model performance for each of the material, and then all of the others are just ways to understand the table, the fact. So that's a summary of all I want to say. So now we can start the town hall meeting part, which we invite all of the teams to present and share what their experience throughout the challenge, what has worked, what has not worked, and that's very interesting. And what are your most interesting discovery? What's your opinion? What's the possible path towards a standard model? What do we need? How can we do better? So in terms of either organizing the challenge or how do we run this open source community in a better way? We are very open, and I'm actually happy if there are other universities who want to lead these efforts, or if you want to host the next MagNet challenge. I've started to think about it. What do we do? What's the next challenge? But I'm happy to hear your opinion, and happy to, if your team, your university is ready to host the next challenge, I'm happy to pass it to you guys. So that's all I have, and I guess I will open it up for question and discussion time, and then we can move on to team presentations. Anyone has any comments? Okay, maybe people are shy, so we will go ahead and